Hey everyone, welcome to this video. We are going to talk about GANs, also known as Generative Adversarial Networks. So in case you're wondering why we should care about generative modeling or GANs in general, let's go to thispersondoesnotexist.com again. And as the website states, none of these people actually exist. They are all generated. And if we look at the bottom right-hand corner, it will say Style GAN 2. And what do you know? We're going to talk about GANs in this video. Let's get started. First off, what is a GAN? GANs are also used to create new data that will be similar to its training data. This is done by having a contest between two neural networks, a generator and a discriminator. Generator creates new data that the discriminator will think is real data, and the discriminator tries to determine if something is real data, e.g. the training data, or data created by the generator, which you can think of as like fake synthetic data. Once the discriminator cannot tell the difference between real data and data created by the generator, this means the generator can now generate high quality and realistic images as we just saw. So for example, our generator will initially have terrible weights and will not generate realistic looking images. Here it generates like a stick figure smiley face, and so our discriminator will say this is definitely fake or not real, or data generated by the generator. But as the generator's weights improve, hopefully it can generate more realistic looking images, and the discriminator will think, well, it's real, and give it a pass. Another way you can think of this, is this. A real life example could be a new counterfeiter and a new inspector. They're both terrible at their jobs. However, the counterfeiter slowly gets better at making counterfeits, and the inspector slowly gets better at detecting counterfeits. You eventually get a counterfeiter that makes good counterfeits and an inspector that is good at detecting counterfeits. But for GANs, once the training is done, we only care about the first half, that we have a counterfeiter that makes good counterfeits. Let's talk about the generator next. The generator is given a vector of random numbers, as we can see here, and creates new data from this. And I remember when I was first learning about GANs, this still seemed like magic to me. I give you a vector of random numbers and you can generate a realistic looking image once the weights are really good. It still seems kind of crazy and like magic to me. So one way I like to think about it is this: lane space. If you give the generator a vector of 256 random numbers, this is like giving a location in a 256 dimensional lane space, as we can see on the left-hand side. In the lane space, locations that are close to each other will create similar images. So these two locations in my example lane space are close to each other, so I'm not smiling too much, and I'm wearing a black shirt in both of these locations in the lane space. Whereas here, it's a bit farther away, so I'm smiling more and wearing a black jacket rather than a black t-shirt. In the lane space, moving in a direction makes a meaningful change. For example, one direction could be how much Kevin is smiling. Another direction could be if Kevin is wearing a jacket. The generator created this lane space right here by seeing many images of Kevin. You could also think of 0.8 or at index 3, right? Index 0, 1, 2, 3. You could also think of 0.8 in this vector of random numbers represents how much Kevin is smiling. Let's talk about the discriminator next. The discriminator is a classifier that tries to determine if something is real data, such as the training data, or data created by the generator, which you can also think of as like fake data. The discriminator can have an output of 0 to 1, where 0.5 is it is not sure if something is real data or data created by the generator. What happens during training for a GAN? So, warning, wall of text incoming. During training, the generator improves at generating realistic looking data, and the discriminator improves at determining data generated from the generator versus real data. So remember earlier on in the video, we initially have a new or novice counterfeiter and a new or novice inspector, and they both slowly get better at the same time. During training, we want to reach an equilibrium where the generator can generate data that has a 50% chance of being classified as real by the discriminator. The discriminator receives real data and data generated from the generator. If the discriminator correctly classifies data generated from the generator as not real data, generator loss increases. On the other hand, if the discriminator incorrectly classifies data generated from the generator as real data or real data as data generated from the generator, discriminator loss increases. When training the generator, do not train the discriminator and vice versa. Otherwise, think of trying to learn to surf where the waves keep changing directions. So I know this is a wall of text, but let's actually visualize all of this in the next slide. So yes, we have a vector of random numbers, pass it to the generator, and of course, let's assume here in this diagram that our generator has bad weights, so it will not generate a realistic looking image. Then we also have real data, pass it to the discriminator, and the discriminator will try to guess for both of these whether they are real data or data generated from the generator. And depending on the discriminator's prediction, we will either have generator loss or discriminator loss. Oh yeah, and in case you're wondering why we should care about generator loss or discriminator loss, in this diagram we have gone over multiple times in the course. Remember that we have a model that we want to have really good predictions or outputs, and depending if these predictions or outputs are good or not, or correct or incorrect, we will have an error/loss, right? That generator loss or discriminator loss, which will be used to update the weights of the model, and hopefully our model has better weights to have better, well, outputs or predictions. Then, after training, we don't need the discriminator anymore and can just use a generator to generate new data. More specifically, we will give the generator a vector of random numbers to represent a location in the lane space, and it will generate images from the lane space. Now, there will be a couple of issues of GANs that we need to go over. The first issue is that they are difficult to train. We have previously learned that we optimize models by trying to minimize loss. So in this diagram to the left here, we can see that we want the smallest loss possible of 0. We will need weight values of 2. However, GANs are also trying to get two neural networks, generator and discriminator, to reach an equilibrium, making GANs difficult to train. It's like a very delicate balancing act, so to speak. For example, small hyperparameter changes like the number of layers we use, the number of perceptrons, the learning rate, etc., could be the difference between a working GAN or a broken GAN. Another issue of GANs is something called mode collapse, which is a really fancy way of saying the generator generates data that is too similar because this similar data is what gets past the discriminator. What does that mean in more simple terms? For example, we want a generator that generates a variety of images of vehicles. However, during training, the generator sees that images of red trucks always gets past the discriminator. The generator does not learn to generate images of motorcycles, vans, buses, etc. So now that we've learned about VAEs and GANs, let's compare the two. In broad strokes, VAEs are less difficult to train, but can generate blurry images, in part due to compression. And GANs are harder to train, but can generate better images. So there are pros and cons to using VAEs versus GANs. All right, that's it for this video. Thanks for watching, See you all in the next one.